In this lecture, we're going to talk about a continuation of the metric system, percent, volume, and density. These are really critical concepts that you need to understand. You're going to be using them a lot. So when we say percent, we literally mean part of the whole. When you talk about, for example, how much of something is left, what you're really saying is what pieces are done or used or gone or missing out of all that was there. I often talk about this in terms of pizza. So if I got a pizza, there's my beautiful pizza drawing. If I have a pizza and I say to you, I ate one piece and I shared a piece with a friend, we would typically say 2/8 were eaten. Well, if I were to actually take 2 divided by 8 times 100%, that would simply just mean that we have some amount or some percent of the pizza that is eaten. In this case, 25%. What's left is 75%. So we have part out of the whole times 100%. That's all we mean with the percent concept. Using this in chemistry, it's no longer number of things present. We have to also take into account their mass. So in this particular case, they're dealing with mass in terms of what it's made of, but we will also talk about it in terms of an actual chemical formula and the individual element's mass. So in this case, bronze is an alloy. An alloy is a mixture of copper and tin. So bronze is made up of copper and tin. If we have some sample or some amount of bronze, we find it to contain 79.2 grams of copper and 10.8 grams of tin. So the question is, what is the percent of copper in the bronze? Well, when we have that amount of copper, that's our part. Oh, that didn't work well. The whole is the copper and the tin added together. Why isn't this writing? So when we say part of the whole or percent of copper in it, we're going to take the 79.2, divide it by the total mass of the whole thing, which is 79.2 plus that 10.8 of tin, multiply that by 100%, we will find that bronze is 88% copper. You will find that we are going to be using percentages as unit factors or conversion factors quite a bit. Whenever we see this percent sign here, you can always assume grams. So what do we mean by that? When we say a percentage, what we mean or what we assume is that it's out of 100. So 25% is the same as saying 25 grams out of 100 grams. All right. So whenever we see a percent, we can assume grams. And this is how we use it as a unit or conversion factor. So let's look at an example. The Earth and the Moon have a similar composition. Each contains 4.7% iron. What is the mass of iron in a lunar sample that weighs 92 grams? Lunar sample meaning from the moon. Our sample weighs 92 grams. This is our given. Okay. The percentage we are going to use as our unit factor or conversion factor. Remember, our setup is always given times the unit factor or factors. Sometimes there's going to be more than one like we saw in the last video. And that's going to equal our unknown or our asked for. Okay, so in this case, remember we like to put it over 1 so it looks like 2 fractions. We're going to have our sample, grams, that's our given. Our unit factor is going to be 4.70 grams per 100 grams. Note the units. We have a sample, so it's amount of iron per the entire sample. So we could say it's 4.3 grams of iron. Now some of you might be wondering, well, Miss Merriweather, why can't we just do this? Why can't we just say 92 times take that percent and turn it into a decimal? Why can't we just do that? My answer is technically you get mathematically and technically you get the exact same answer. The problem in chemistry is that this doesn't always work. It doesn't always work. So get out of the habit of doing that so you can get into the habit of setting up the math correctly. Because just being able to multiply by a percentage turned into a decimal doesn't always work. Volume, we have a couple of different ways we can calculate volume. The first one you're probably very familiar with. This volume equals length times width times thickness or height, right? You've probably done that in math a ton. Same with chemistry. Length times width times height. So if I have some object that's 3 centimeters by 2 by 1, my beautiful cube there, oops, there we go, beautiful cube. We're going to pretend it's even. If I said it was 3 by 2 by 1, what we're saying is length times width times height is our volume. So we could simply say 3 times 2 times 1 equals 6. But remember, just like with our x's, x squared times x squared times x squared is x cubed, as are the centimeters. With solid objects, we're going to be using the unit of centimeters, cubic centimeters. With liquids and gases, we're going to use milliliters. One thing to note, 1 cubic centimeter is equal to 1 milliliter. You got to know that and remember that. Here's just another example. If this were 10 by 10 by 10, which it is, we can say that's 10 times 10 times 10, right? So 10 times 10 times 10 is 1,000. And that's going to be equal to 1 liter. We could also say 1,000 milliliters is equal to 1 liter. Now, cubic liquid volume conversion, how do we get from cubic centimeters to, milliliters? Well, that's easy. But here's the thing we got to talk about. When we're saying, all right, let's just say we were going to convert cubic inches, I'm sorry, wow, words are hard today, cubic centimeters, and we wanted it in cubic inches. two things are happening. The first thing is, yes, the relationship is still the same. 1 inch equals 2.54 centimeters. We know that to be true. So if I'm going to convert cubic centimeters, then what's going to happen is I'm still going to use this, but I have to do it 3 times. So if you'll notice here with the math, the very first time I multiply by my conversion factor, here's time 1. That only cancels with 1 of the cubic centimeters. So once I did this math, what I would really be left with is, let's see, 498 divided by 2.54. I would be left with 196 centimeters squared. So now I have to do it again. All right, not centimeters. Yeah, centimeters squared inch, sorry. All right, so now if I do it again, after the second one, another cubic centimeter is canceled out, and I'm left with 77.19 centimeters inches squared. Because now I've multiplied it twice and canceled centimeters twice. Finally, my third inches in centimeters gives me this answer. You'll see the centimeters canceled, and this is my third inch. So now we have inches cubed. Another really easy way to do this, you just got to make sure you use parentheses in your calculator, is just taking that 498 cubic centimeters over 1 and multiplying it by 1 cubed inches cubed divided by 2.54 centimeters cubed. The whole thing is cubed. Either way that works better for you, you can do. You just got to keep doing the math until all of the 1 unit cancels out and the new unit is there. The next kind of volume we have is volume by displacement. Volume by displacement literally means I have some uneven object, maybe a rock from the parking lot, or a pine cone, or I don't know, a pen or something that we just can't measure length times width times height, but we still want to know the volume of it. The way to do this the easiest is to get a graduated cylinder and fill it with water to a certain point that you've measured, maybe 25 milliliters, and then you put the object in it. The amount of water that the object displaces is the volume of that object. So the volume of the object is equal to the final volume minus the initial volume. So here's the example. Here we have 50 milliliters in a graduated cylinder, and we have some piece of jade. Jade is just a stone. We put it into the graduated cylinder, and you can see the new volume is 60.5 milliliters. So that means the volume of the jade is equal to the 60.5 milliliters minus the 50 initial milliliters, because the amount of water that the object displaces is equal to its volume. Density. Density we're going to use 3 different ways. Okay, we're going to use density as a definition, an algebraic expression, and a conversion factor. So what do I mean by that? Well, first of all, this is the equation for density. Okay, the equation for density is the mass divided by the volume. By definition, It is a certain amount of mass divided by a certain amount of space. So 1, it's a definition. Second, an algebraic expression. And third, it's a conversion factor or unit factor. All right, so how do I know it's a conversion factor? You have a compound unit. The unit for mass is grams. The unit for volume is either cubic centimeter or milliliter. So if I have some number, grams per mil, for example, when you have that compound unit, you should know you should be able to use it as a unit factor or conversion factor. All density is again mass per space. So the higher the density, the higher the mass in the same amount of space. So if you were to compare ice, water, lead, and osmium, you will see clearly that the density is increased and is highest with the osmium and lowest with the ice. That's because for ice, there's less stuff or less mass per certain amount of space. In this case, 1 cubic centimeter, because we're comparing all of these to 1 cubic centimeter. Whereas osmium, for 1 cubic centimeter, has a much larger amount of mass per space. Here are just some examples of densities of very common stuff you're going to see. You need to memorize pretty much everything you have to memorize as far as constants in here is going to be for water. So you need to memorize ice, water. I don't see water on the list. Here's water. And this is a typo. This is incorrect. It should be 1.00 for water. Grams per mil. And then finally, water vapor is not on here. I don't see it. I'll get that for you, but you're going to have it for steam or water vapor. Okay. We can estimate density by simply putting things, together. So if we know that we have 3 different liquids, you can clearly see they're spaced out. Maybe this is oil, vinegar, and water. Maybe it's an ethyl alcohol and oil and water. The point is the 3 liquids, 1, 2, and 3, clearly have different densities because they're layered. We see that in salad dressing. We see it when you try to mix oil and water. Now, if I want to compare the solids I put in there, some go all the way down to the bottom, some stay in the middle, some go to the top. What this means is that S1, for example, has a lesser density than water, but a higher density than whatever liquid 1 is. Where S3 has a higher density than water and whatever liquid 2 is. And we know that because it's way at the bottom. It's not floating in the middle. So if I were to ask you, what is the density of a platinum nugget that has a mass of 224.50 grams and a volume of 10 cubic centimeters? You would say, okay, density equals the mass divided by the volume. They told us the mass. Here's the mass. And then they're going to tell us the volume, 10 cubic centimeters, volume. You do the math and you simply just get 22.5. Now, note, technically this would have been, technically this would have been 2.450, but we are limited to 3 significant figures because when dividing, we're limited by the number in totality that has the least amount of significant digits, in which case that's the 10 right there. So 1, 2, 3, 5 is 5. So we round the 4 to up. That's where this 5 is coming from. Using it as a unit factor, here we go. Let's see how that works. An automobile battery contains 1,275 milliliters of acid. If the density of battery acid is 1.84 grams per mil, how many grams of acid are in an automobile battery? Well, this is our given. And this is our conversion factor. How do we know it's a conversion factor? It's got compound units. Okay, now we should be immediately taking this 1.84 grams per mil and turn it into so it looks like a fraction. All right, so here we have our given. We're going to put that over 1. You put it in. You put the milliliters in so that they cancel, like so. Grams needs to go up here, and the number never leaves our buddy unit. Okay, calculate out the math, and there you go. Temperature. So we are going to talk about Fahrenheit, but we're almost never going to use it. In chemistry, these are the two temperatures that we use. Fahrenheit we know exists because that's what we use. That's the English system. Then Celsius, which is metric, and Kelvin, which is the absolute temperature scale. Now, when we talk about temperature, we're talking about degrees of hot or cold. I will read this. 212 degrees Fahrenheit, 100 degrees Celsius. For Kelvin, I drop the word degrees and I just say Kelvin, 273 Kelvin, because it is the absolute scale. So you have to know for water that you probably know for the English system in Fahrenheit that it freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit. You need to worry about the Celsius scale. Water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. So when converting from Celsius to Fahrenheit, this is your equation. Degrees Celsius times 180 divided by 100. You'll note the degrees Celsius cancels, and you're left with Fahrenheit. For Fahrenheit to Celsius, this is your equation, but this is the one you are responsible for. Know these and reference these, but this is the one you're responsible for me, converting from degrees Celsius to Kelvin. And simply all that means is whatever your degree Celsius is, adding 273, and you get and then you get the temperature for Kelvin. So if I had 25 degrees Celsius and I wanted to go to Kelvin, I would say 25 degrees Celsius plus 273 equals 298 Kelvin. Again, this is just converting from Fahrenheit to Celsius, and then again to Kelvin. So if you're told your body temperature is 98.6 degrees Fahrenheit, what is it in degrees Celsius and what is it in Kelvin? The first thing I'm going to do is I'm going to use my formula, this one right here, and say degrees Fahrenheit minus 32 times 100 divided by 80. And you get 37 degrees Celsius. To get to Kelvin, I'm simply going to add 273 to it. Okay, so plug it in, add it together, you get 310 Kelvin. Finally, I just want to talk about heat and temperature. They're two different things. We often use those words interchangeably, but we're not using them interchangeably this time. We might say, gosh, it's so hot outside. What's the temperature? That's a way of just saying, gosh, it's interchangeable. When we talk about heat and temperature, heat is what we refer to as total energy present. We're going to refer to heat as Q. That's going to be its variable, if you will. Temperature is the average energy of particles in a system. So when you have a thermometer and it's measuring 88 degrees outside, that's the average energy of the particles in a system. We can express the units of heat as joules with a capital J or calories with a lowercase c. This is not food calories. Okay? Food calories is a capital C for its unit. This is heat or energy. Calories. Okay? Lowercase c for heat or energy calories, capital C for food calories. By the way, heat and energy, we can interchange those words. So here's how you can talk about, or here's how you can better understand how heat is different than temperature. If I had a coffee cup full of hot, right out of the pot, hot coffee, or I had the entire carafe, if one had to get spilled on you, which would you prefer? You should be thinking the coffee cup. And the reason for that is because there's less hot coffee in it than the whole entire coffee pot, right? The energy in the larger volume of liquid will do twice as much damage than the smaller volume of liquid, even if they are at the exact same temperature. And lastly, we're just going to talk about specific heat. Specific heat is really important. It's the amount of heat needed to raise the temperature of 1 gram of something by 1 degree Celsius. So how much heat is necessary to raise the temperature by 1 degree Celsius per 1 gram of whatever the substance is. Every single thing in the universe has a very specific heat that never changes, but it is specific to that particular compound or formula or item or element or thing, okay? Water's specific heat is 1.00 calories per grams degrees Celsius. We have a compound unit with specific heat. So guess what we can use specific heat for? If you said unit conversion or conversion factor, you are correct. The last equation that you need for this, the equation to solve for specific heat is Q equals the mass times the specific heat times the change in temperature. Okay, Q is the heat, capital C subscript S is the specific heat, mass is mass, delta T is change in temperature. Delta T is the final temperature minus the initial temperature, and it is always positive because we're just looking for the change. Now the other equation for this for heat you'll need is Q equals the mass times what we're going to call a heat value. and we will just write this down, have it kind of in the back of your brain. We'll be talking about heat values in a later unit. So this wraps up our Unit 3, and hopefully you guys will be ready to go in class to work these problems. If you have any questions, please let me know.